Let's get that going. And let's get started. So the point of today is to transition from formal proofs, where we rigorously write out every single line of reasoning and every single rule of logic that we're using as we're using it, to informal proofs. Those of you who have taken proving math classes, the types of proofs we do in a math class. Those are much more informal proofs, not near as precise. And so the whole point of chapter 7, I'm pretty sure it's chapter 7 that we're on. The whole point of chapter 7 is to help you make this transition from formal proofs to informal proofs. And we're using as our medium arithmetic, basic arithmetic. So we're going to take the axioms on the real numbers and we're going to do some informal proofs with them to get you comfortable with informal proofs. So this will be the medium for informal proofs. And there will also be another axiomatic system that we go over. So this is now going to be our fourth axiomatic system. Because the major use of logic is this construction of axiomatic systems. That's what we end up doing with it when it's all said and done. Every single theoretical body of knowledge that you can come up with is an axiomatic system and / or some combination of axiomatic systems. Doesn't matter what field you're talking about. You talk about something like Newtonian mechanics. We take as our axioms Newton's laws. Together with, we get to use all of analytic geometry, which uses the axiomatic system for geometry, and calculus. So we presuppose the axioms for calculus, for geometry, combine those two, throw in Newton's laws, put it all together in a big mix, and that's what we mean by Newtonian mechanics, those things that we can presuppose. So every single theoretical body of knowledge, doesn't matter what you pick, it is either an axiomatic system and / or some combination of axiomatic systems. Make sense? So that's why it's stressed so much that we're doing axiomatic systems. That's the main thing we use logic for, is the construction analysis of axiomatic systems. So we're going to do an analysis of another one. We've done weak preference. We did one with a logic, maybe you'll recall it. The symbols in it was, we used a plus symbol for or, we used a prime symbol for not, and then we used just a predicate, P of x, and that meant x is true. That was kind of a weirder one. One that I didn't tell you what the term, give you any intuition for the terms before we start proving things. I came back later and told you, now here's how you can think about it. You remember that one? Yeah. So we did that one, and last time we did some basic group theory. And so now we're moving into arithmetic, some basic algebra stuff. The stuff you assumed if you ever did a pre-algebra, algebra 1, algebra 2 course. What were the fundamental things you were assuming? What were the axioms for that course? They're these axioms right here. Okay, so let's jump into our system. What's our system? Notice it has 15 axioms. It's going to be a lot to take in. Fortunately, we're very, very, very familiar with most of these, and almost all of these are just going to appeal to your intuition. The hard part when we do these early on proofs is to make sure you're just using the exact information you're given and not presupposing some other information that you're already comfortable with. Like you're comfortable with the fact that 2 plus 2 is 4. Can you prove it? Not likely. Let's get you to the point where you can prove 2 plus 2 is 4. Wouldn't that be nice? All right, and we use these axioms to do it. So let's jump into these and make sure that they all make sense. So, in our axiomatic system, we need to specify the domain that all our terms are going to come from. So our domain for this is going to be that fancy R with an extra line. It turns out that fancy R with an extra line, if you don't know what it is just a symbol for all numbers. And if you know what complex numbers are, you already know what that symbol is, so don't say anything. If you don't know what complex numbers are, then that just means all numbers, and you're good. Any number you can think of. 1/2, 10 trillion, 0.00001. Okay, so that's going to be our domain of individuals. All our terms are going to be numbers. We call them real numbers. So if I say number, a real number, basically the same thing. Okay, so let our domain of individuals be R, that fancy R, and we're going to discover things about R. So drop all that knowledge you have about numbers to the side for now. R right now we know it's just a set of terms and we don't know anything about it yet. And we're going to discover things about R. And we're going to discover that it has all the numbers that you know and love. So let our domain be that fancy R. Let that fancy symbol, we call it plus, and that fancy symbol, we call it times, be binary operators. So they take two terms and they spit out a term. Binary operators on R, so they take two things in R and they spit out something else in R. So I'm guaranteed if I close my eyes, I grab two things out of R, and I put them through the plus, it's going to spit out something else that is in R. Same with the times. So the plus and the times are binary operators on R. And let that symbol, we're going to call that the less than relation, and let that be a relation on R. So this is a relation. You give it two terms out of R, and it spits out true or false. Remember, a relation is a two-place predicate, a predicate that takes two terms. Let's remind ourselves really quick. Proposition and predicate, make sure we got this clear. We can't keep struggling on this. What's a proposition?
It's a statement that's true or false.
It's something that's true or false, not both. Right? And what's a predicate?
Proposition value function.
That's what we say, a proposition valued function. Now if that sounds like a mouthful or sounds like she's using weird jargon, a predicate is something that takes in terms and spits out true or false. A real valued function is a function that spits out real numbers. A proposition valued function is a function that spits out propositions. You give it a term, it spits out proposition. Proposition is something that's true or false. For the programmer, it's a Boolean valued function, a function that returns a Boolean. Okay, so we have less than is a relation on R. So it's a predicate that takes two terms. And you already have great intuition for all these things. All right, such that. So R, our domain is R, and plus and times and less than are all operations and relations on R, such that these 15 properties are satisfied. And that's it. That's everything we assume in your algebra course. Let's go over these 15 properties. The first one is that for all x, y, I don't know if we've used that symbol before in this class, have we? That means in. For all x, y in R, for any two elements in R, in our domain, before we just wrote it like that, and it was understood that x and y were elements in R, in our domain. Now I'm specifically saying x and y are in our domain R. So for any two x and y in R, or for any two real numbers, x and y, x plus y is equal to y plus x. Or in other words, addition is commutative. X plus y is the same thing as y plus x, for any two real numbers you choose. Next. For any two real numbers x and y, x times y is equal to y times x. So whatever that dot symbol is, it's commutative. That we're guaranteed. Third one. For any x, y, and z in R, this is basically the exact same one that we had for group theory. For any x, y, and z in R, x plus y plus z is equal to x plus y plus z. In other words, if you add the y and z together first, and then add them with the x, you get the exact same thing as if you added the x and y first, and then added the z. And we call that property associativity. Or in other words, addition is associative. That's a high-level way of saying this. Next one. For all x, y, and z, x times y times z is the same thing as x times y times z. Or in other words, multiplication is associative. Okay. So what do we do when we get pluses and timeses together in one expression, one equation? How do we use them together? Here's how. This one we call the distributive property. For all x, y, and z, x times y plus z is the same thing as x times z plus y times z. Where you do the times first.
Yeah. Do you need the parentheses there?
We're about to make sense of that here in a second.
Why is it not y times x?
X? Because I'm crazy. Thank you. Now someone's paying attention. X times y, x times y, x times z, x times z. That was a test. You get an A, the rest of you fell. All right. Thank you. Okay, let's say it again. X times, I probably even said it wrong when I read out loud. x times y plus z is the same thing as x times y plus x times z. Those are the same thing. Now, it is really tedious to be writing these parentheses all the time. So you and I are going to come to an agreement right here, right now. Anytime we have plus and times together, and if we don't put any parentheses in there, it's agreed between you and I that we will always do the multiplication before the addition. And that way I don't need to go crazy writing parentheses. So if I write 3 plus 4 times 5, this is not equal to 3 plus 4 is 7 times 5, 35. No. It's going to be equal to 4 times 5 is 20 plus 3 is 23. And that's just an agreement we're coming to right now to save me from having to write a billion parentheses.
Is there a formal way that they express that in the axioms, or is that just...
No. It's something that you need to specify. It's a matter of convention. It's not a fallout from these. If you were to be completely rigorous in all your proving, you'd put all your parentheses in. We're also very fast and loose, and we write things like 1 plus 2 plus 3 equals 6.
Right.
Strictly speaking, that's nonsense. You either have to have parentheses here or parentheses here.
Right. That makes sense.
So we're going to write things that, strictly speaking, are nonsense because we get lazy.
It doesn't matter.
Right. It turns out these things don't matter. You understand what I'm saying. And so we agree amongst ourselves that we're not going to require ourselves to be too rigorous. We get it. The point is, enough information that you could be rigorous if you had to.
Right.
That's always the goal. So be as lazy as we can without losing the ability to still be as rigorous as possible. If we need to. Okay. So we talked about the distributive property. Okay. Now, our identity elements. Axiom 6 says we have an additive identity element in R. There exists something, we call it 0, in R, such that for anything in R, x plus 0 is x. Or in other words, 0 is the additive identity. If you add with 0, you get back identity. You get back yourself. You get back the thing you added with 0. So 0 is called the additive identity. That's what Axiom 6 says. High-level language, 0 is our additive identity. That's a high-level language version of it. High-level language version of this is 1 is our multiplicative identity. What does this one say? It says that there exists something in R, we call it 1, such that for all x in R, x times 1 always gives us back that x. Anything times 1 is just that thing. X times 1 gives us back identity, gives us back ourselves. 1 is called the multiplicative identity. Okay, so 6 and 7, we have an additive identity and a multiplicative identity. All right, what does Axiom 8 tell us? It tells us we have an additive inverse. It says for any x, there exists some y such that x plus y gives you back the additive identity. For any x, for any number you choose, I can always find some other number, such that when we sum them together, we get additive identity. Similarly, this one. For any x you choose, as long as you don't choose 0, where x is not 0, I can find a y such that x times y gives us back the multiplicative identity, or 1. So for every x, if x is not equal to 0, then there exists a y such that x times y is equal to 1. Good? This is very much related to the fact that we can't divide by 0, in case you're wondering why that. That's what stems from it. Okay, next, our lesson operator. For all x and y, if x is less than y, then it is not the case that y is less than x. Good? Next, lesson is transitive, is what this one says. For all x, y, and z, if x is less than y and y is less than z, then x is less than z. All right, next. For all x and y, if x is not equal to y, then it's either the case that x is less than y or y is less than x. Good? Next, for all x, y, and z, if y is less than z, then y plus x is less than z plus x. If y is less than z, we can add the same number to both sides of the inequality and it stays the same. So if y is less than z, add x to both sides, and the inequality is still true. If you have less money than me, and someone both gives us $100, you still have less money than me. I don't know. Obvious? Last one. For all x, y, and z, if x is greater than 0, or in other words, if x is a positive number, and y is less than z, then y times x is less than z times x. Or in other words, if we have an inequality, we can multiply both sides of it by a positive number and it doesn't change it. If I have more money than you, and then both of us doubles our money, I still have more money than you. Or if I have more money than you, and both of us halves our money, I still have more money than you. As long as we take our money, multiply it by the same positive number, the inequality is still going to be true. Good? And then finally, the non-trivial axiom is what that one's called, which is 0 and 1 are actually different numbers. They're not secretly the same number. And we have to take that as an axiom. Good?
Why is it called the non-trivial axiom?
Because if you allow 0 to equal 1, then the only number in your system is that number. And so it turns out all this is just saying things about 0.
Yeah, it just seems like a funny name. It's like, this is an important axiom or something. It's not useless. It's just weird. I wonder where that name came from.
It's kind of like this is the axiom that makes our whole system isn't useless.
Oh.
Because then all we're talking about is 0 the whole time.
And it seems like such a easy thing to understand. Like obviously 0 is not 1, right? So it's not trivial. It's not a trivial little fact. I think is what they're trying to say.
Well, it's what makes the system non-trivial.
Right.
A system about one thing.
I see. Okay.
Okay. Now, thus far, what do we know about this fancy R right there?
You know these things.
We know all these things, but what do we know about what's in there?
You know 0.
What terms do we know are in there?
0.
So far, we have 0 and 1. That's it. That's all we know about R so far. So whatever R is, it's equal to, it has 0 in there, it has 1 in there, and it has who knows what else in there. But so far, all we're guaranteed so far is 0 and 1. Okay? Let's briefly make sure that we're comfortable with the primitives of our system. The primitives are the undefined terms, the things that we have no definition for. So the things that are undefined here are plus, multiplies, less than, 0, and 1. We have 2 undefined operators, 1 undefined relation, 2 undefined terms.
I thought we defined 0 as like the additive inverse, and 1 is multiplicative. That one.
This isn't a definition, it's an axiom. It has meaning. We know what 0 is, but it's not defined. To say what's the definition of 0 is a bad question. So all our definitions from here on out will be in terms of these primitives. But we need some starter words to begin defining things with. Right? That's why I can't give you a French dictionary and say, here, learn French. Because every time you look up a word in French, you get a bunch of other French words. You go look those up, and you get a bunch of other French words. And so you can't just use definitions to ever come to understand what terms mean. You need to somehow understand what something means without a definition, like through axioms, and then you can create definitions with those things.
So isn't this actually just the rational numbers? You don't have the completeness axiom.
Correct. So we're not going to get all of R, and we're not going to have the completeness axiom. So technically, you can think about it as just being the rationals, and we're good.
Okay.
But we're not going to worry about that detail. If any of you ever take real analysis from me, then we'll worry a lot about that detail. Okay, and I wanted to get you comfortable with names for those because as we do the rest of this, the axioms are going to be off the screen, unfortunately. Okay, so I had a skinny marker that seemed to be good on ink. And it's on the desk. Okay. Little bit about proofs, theorems, lemmas, and corollaries. Because you're going to see me write all three of those up here. I'm going to write proof, I'm going to write theorem, I'm going to write core for corollary, and I'm going to write lemma for lemma. What's the difference between all these four things?
Are you asking or?
Yeah.
Well, a corollary is basically a theorem that comes really easily.
So
after
maybe
the
let's start with
result.
a theorem then, before we get to corollary.
Well, theorem is a logical proof.
Okay, so what's the difference between a proof and a theorem?
I guess a theorem is the result. It's the result of a logical proof.
Okay, now. There isn't a difference, really. These are all just jargon that we create to talk about how important something is or how it happens to come. So corollaries, lemmas, theorems, and proofs are all just proofs. We use proof if we're saying, I'm going to show you something, but it's pretty useless. We're not going to use it again. That's a proof. So anytime you solve like an exercise in your book, you were told in your algebra class, if 3 plus x equals 7, what does x equal? You proved that if 3 plus x equals 7, then x equals 4. That's a proof. Pretty useless proof. So we just call it a proof. Theorem, we're saying this is something that's pretty useful. It's a pretty useful proof. You're probably going to use this a lot. But it's a vague notion of what's useful, what's not, who's to say. A lot of it's just naming. A corollary, like Levi said, is something that you basically get for free from the preceding theorem. So you prove something, and then the corollary is something that almost obviously follows from it, but it's still just a proof. Corollary is just a name, still just a proof. And lemma is something that is usually an easy proof that we're doing in preparation for a theorem. I don't want to prove this theorem yet because there's this useful little fact for this theorem, and I want to prove that useful little fact first, and then we'll do the theorem. So proofs, corollaries, lemmas, theorems, they're all just proofs. Or they're all just theorems, or they're all just lemmas. Well, sounds a little bit weird to say.
Explain a lemma again.
But there's no real difference between them.
Can you explain a lemma one more? Of what?
So
Why?
lemma is something that is a proof that we prove really quick to prove a theorem. A corollary is something that immediately follows from a theorem. So an easy proof before a theorem, that's a lemma. An easy proof that immediately follows a theorem, that's corollary. Theorems, useful proofs, and then proof is just proof. So they're all just proofs. And sometimes people get confused by the different terminology for a proof.
And the definition is not there.
Definition is completely different. So when I told you every axiomatic system is composed of only 4 things, I said you have your axioms, your primitives, sometimes we call your primitives your undefined terms, your definitions, and your theorems. I'm being pretty vague with theorem there. By theorem, I mean anything we prove. So when I said theorem in that sense, I meant anything you prove in the system. So maybe I should say proofs instead of theorems, but that's not typically the way it's said, so I say it the way it's said. So just don't want to get confused by verbiage there.
Can we still add things to the left and right hand side of the equations like we were in the last class?
Yes, we proved from logic, this was a consequence of logic. If A is equal to B, then A plus C is equal to B plus C. This implies this. That is not something you prove in arithmetic. That's not something you prove in algebra. That's something we prove in logic. This is the case for any operation. For plus, for times, as long as the operation is well defined. For compose, if we're talking about functions. For matrix multiplication. For any operation you can think of. It's always the case. So that's a consequence of logic. And we will definitely be using that here. Use it a lot. Okay, so let's get started. So first I'm just going to prove a little bit of quick stuff that's not really, the author doesn't bother with. I'm just proving it just because. Kind of dip our toes into the system a little bit. So first thing I want to prove is that 1 plus 1 is not equal to 1. You with me?
Mm-hmm.
So I know that 1 plus 1, whatever it is, it has to be a real number. Because 1's a real number, and 1's a real number, and I'm guaranteed that anytime I take 2 real numbers and I add it together, it's also a real number. So whatever 1 plus 1 is, I'm guaranteed it's a real number. Now let's do a quick proof that 1 plus 1 is not equal to 2. Proof, or 1 plus 1 is not equal to 1. 1. Assume by way of contradiction that 1 plus 1 is equal to 1. With me? Now what are we going to do? Looking over at our axioms, what might we do?
Use axiom 6.
Use axiom 6. Axiom 6 says that 0 plus any, 0 is the additive identity. Maybe not that one. Maybe you had an idea on where to go there.
Maybe axiom 8.
Axiom 8. Axiom 8 says for any real number there exists some other real number such that their sum is equal to 0. So I am guaranteed to, by axiom 8, comma, there must exist some number, I'll call it y, there must exist something in R, some real number, call it y, such that y plus 1 is equal to 0. I'm guaranteed that by axiom 8. 1's a real number. For every real number, there must exist some y such that y plus that real number is equal to 0. That's using axiom 8. With me?
Yeah.
Okay, so then what?
You would add y to both sides of the equation.
I can add y to both sides of the equation.
Oh.
That's using logic. It's not using one of our axioms. From logic, we know if A equals B, A plus C equals B plus C. I can always add the same thing to both sides of the equation. Do we remember how this follows from logic? From the law of identity?
Isn't that what you call the principle of extensionality?
It's two things in one. First, we use the law of identity. The law of identity says everything is identical with itself. Oops. A plus C is equal to A plus C. That's true by the law of identity. Now, if A is equal to B, then the law of existentiality says I can substitute in A's for B's. So substitute in, not that one, substitute this A in for B. And there we go, we get it. Okay, so that's how we prove that. So we can definitely use that fact. So I can add y to both sides. So then, 1 plus y is equal to 1 plus y. Right? Now what?
Well, 1 plus y is equal to 0. You can also use the associative property, so you get 1 plus 0 is equal to 0.
Right. So then, using associativity, then by which one's that? Is that axiom 1 for associativity, axiom 3 for associativity on addition?
Yeah.
Yeah.
By axiom 3, I know that 1 plus 1 plus y is equal to 1 plus y, right?
Yep.
So, rewriting this now, I know 1 plus y is equal to 1 plus y. So I replace that with that using associativity.
It's equal to 1.
It's equal to 1?
It's equal to 1 plus 0.
Oh, right. That will be our next thing.
Wait a minute. You said it's equal to 1 plus y.
I just used associativity on this so far. I rewrote 1 plus y as 1 plus y.
And then on the other side of the equation.
I left it alone.
Oh, okay, yeah. Right, because it's a lot. It's a contradiction. That's great.
Okay, so far just used associativity. Now, I'm using our rule of identity. I know that y plus 1 is equal to 0. So I can substitute that in for y plus 1 down here. Oh wait, I have 1 plus y. Then by axiom 1, I know addition is commutative. I can write 1 plus y plus 1 is equal to y plus 1. Change the order, change the order. Kind of tedious walking through every piece of logic that you use.
Yeah.
6. Then, by rule I from logic, the rule of identity, since y plus 1 is equal to 0, we get 1 plus 0 is equal to 0, right? Now what is 1 plus 0?
It's 1.
How do you know?
Because of axiom 6.
Axiom 6. We'll see if he was lying. He was correct. There exists a number 0 in R such that for any x, x plus 0 equals x. 1 is a number in R, so 1 plus 0 is equal to 1. Then that was axiom 6, comma, 1 is equal to 0. Now what?
1 is not equal to
Axiom
0.
15.
Axiom 15.
Right. 8. By axiom 15, comma, 1 is not equal to 0. Contradiction. We've got 1 is equal to 0 and 1 is not equal to 0. Therefore, the thing we assumed must be false. 9. Therefore, 1 plus 1 is not equal to 1. We did it. 1 plus 1 isn't 1. Maybe it's 0 though. We won't prove that, but it's also not 0. And we can prove it's not 0.
I hope so.
So it's not 1 and it's not 0. So it's a different real number. We found a different real number. And so we're going to make up a symbol for it. I'm just going to write some random squiggly thing. We write that random squiggly thing. We call it a 2. We define 2 to be 1 plus 1. And so we found another real number, namely 2. And similarly, we can define 3 now. 3 is 2 plus 1. And 4 is 3 plus 1. And 5 is 4 plus 1. 100 is 99 plus 1. And we define all these things. And we can go through all the work of showing that each one's different from all the other ones. That would become kind of tedious. Those of you who are familiar with proof by induction might understand how we could always prove that the next number is different from all the preceding numbers. All in one go. We won't do proof by induction in this class, I don't think. Maybe at the very end.
How do mathematicians, do they have like a function or what? How do they represent their system? We have a base 10 system to represent all these numbers. How do they encapsulate that logically that you can just keep going up and shift the place value?
It doesn't matter that we happen to be using a base 10 system to write these. If I were writing these numbers in binary, it wouldn't change anything.
Sure. So how do we encapsulate the different systems?
We just define the new symbol as we go.
Yeah, there are like 10
Just you do as you go.
I'm defining it as I go.
But you and I have a way of understanding how it works.
Right, so we could create we could take the time to create some rigorous recursive definition for how we define the predecessor of a number. Or not the predecessor, the successor of a number. And we could walk you through, if it ended in this symbol before, a 1, rewrite it, but this time the ending symbol is a 2. If it ended in a 2, ... If it ended in a 9, replace it with a 0, and increment the next one.
But ultimately, the whole number is a single symbol representing a
Ultimately,
previous number plus 1.
you end up with a symbol representing a number.
How do you
And what symbol you use, the fact that we use that squiggly thing there for that, doesn't matter.
So
how
1,000
do computer
is
scientists do it? How do computer scientists do it when they're building a computer? Like when a computer knows how to do that.
Yeah, you just increment it up.
Talking about converting from binary to base.
No, I'm talking about if you give a computer 10 trillion and then you add 1, it gives you 10 trillion and 1.
Yeah, and just increments.
How does it know how to increment?
If it's a
So
1, it sets it sets the next one.
you
opposite
can learn the
or-
logic for that. You can learn how an adder works, but that's getting into the circuitry of how you add. And you can learn the circuitry for that if you get CS degree. That's one of the things you'll do.
It does exactly that. But yeah, it's really way simple.
It's a lot simpler than you think, and I bet that you could find an easy YouTube video that showed you like all the circuits for like something that can add 4-bit numbers. Something with just 4-bit numbers would be pretty straightforward. Anyways, so there we go. So now we have all these numbers defined. And so you now know the definition for all those numbers. And if I ask you for the definition of 10,000, you can tell it to me. It's 9,999 plus 1. That's 10,000 by definition. What's the definition of 5? 4 plus 1. Definition of 4, 3 plus 1. Definition of 3, 2 plus 1. Definition of 2, 1 plus 1. Definition of 1, Bad question. There isn't a definition of one. It's like asking me which of my mansions is my favorite. Bad question. I don't have any. All right. Next. Promise you we proved 2 plus 2 is 4. Let's now do the proof. 2 plus 2 is 4. Let's go through this. We could probably scribble down underneath this. Therefore, 1 plus 1 is not equal to 0. Square box filled in, and thus it is demonstrated. Right? Yeah. He's good. So we're all good. Okay, let's try it out what 2 plus 2 is, really quick. 2 plus 2, what does that equal?
Equals 1 plus 1 plus 1.
Yeah, what's the definition of 2? 1 plus 1. So this is the same thing as 2 plus 1 plus 1. Right?
Mm-hmm.
By associativity, I can rewrite this as 2 plus 1 plus 1. What is 2 plus 1 by definition?
3.
It's 3. 2 plus 1 is 3 by definition. So this is equal to 3 plus 1. What is 3 plus 1 by definition?
4.
4. Whew, we did it. 2 plus 2 is in fact 4. And now hopefully you see how you can prove some really basic addition problems. It'd be really tedious, but you could easily prove something like 5,226 plus 79 is whatever. Yeah, that's how you do it. Very tedious. But now you know. Okay, so those were just for fun to give you a first taste of the system. Now we'll do the first proof that the author actually does. Theorem 1. We're going to prove that for all x and y, if x plus y is equal to x, then y must have been equal to 0. Or in other words, there's only one additive identity element. This is almost identical to what we proved in group theory. In group theory, we proved that our identity element was unique. This is the exact same proof, but now with addition. All right, so let's prove that. Over here, theorem 1. We're proving that for all x and y in R, then if x plus y is equal to x, then y is equal to 0. Right? Let's do one proof the full logic way, and then from there on out we'll do informal. So I'll prove this one twice. Once the logic way, and then once the informal way, to give you some contrast. And then we'll do the rest informally. Informally is more like how I did this. Oops, kind of jumped the gun. All right, so we'll do one somewhat completely. I'm not going to write out all the universal specification on the axioms. We'll just do it. Okay, so we want to prove this. We're proving on implication.
So we assume
To prove an implication, you start by assuming the antecedent.
Yeah.
Show that implies a conclusion. So we have as a premise x plus y is equal to x. This is a premise. It's only dependent upon itself for its validity. And it has 5 variables, x and y. Okay, now what? We're trying to get y is equal to 0, right? How can I get a 0 in this thing to show up?
You could, which one is it, number 6?
Yeah, Axiom 6.
And then you would, well, you can use your logic law to
Axiom A.
Yes.
No?
I know that for any number, x is a real number, there must exist some other number, we'll call it z this time, such that x plus z equals 0.
Okay. I thought you were just going to add a 0 to all sense.
So 2, I know that x plus z is equal to 0. And this is coming from axiom 8. And it's only dependent upon axiom 8 for its validity. So I know that there exists some number, call it z. We just barely did existential specification on axiom 8 is what we did there.
And that means z is not flagged.
No, it won't be.
It's specific.
Yeah.
It's a constant now.
It came from an axiom, and so it's not going to be flagged. Because we would have first written down the axiom, and then the next step would have been existential specification and universal
So
specification.
we're really skipping steps.
Yeah, so we're skipping 2 steps. But we've done those steps a lot. Okay, so now z is a number such that x plus z equals 0. That's what z is. Okay, so now what am I going to do?
You're going to combine it with the first line. Oh, wait.
I'm going to take this, and I'm going to add z to both sides.
Yeah.
So 4, or 3. Then I know x plus y plus z is equal to x plus z. And that was using our theorem of logic. I don't remember what we called that theorem of logic. We'll just say logic here. Whatever that theorem of logic was. And so this is dependent now upon
1 and 2. Or axiom 8 and line 1.
we're using 1, x, y, and we are using that particular z. So, and axiom 8. So that's what we're dependent upon for our validity. Wait a second, we use logic. So we're also dependent upon logic.
But you don't have to write that.
Well, no joke, we're always dependent upon logic. We don't write that as a dependency. Okay, next, 4.
Now you would do your substitution thing.
You would
right?
use axiom
Almost.
3.
Axiom 3.
Oh, yeah.
So I know that x plus y plus z is equal to x plus y plus z. That is axiom 3. And that's always true for any 3 things. That's only dependent upon axiom 3. Okay. Now, I'm going to use substitution. I know this is equal to that, so I can substitute this in for that, right there. So I'm going to use my rule of substitution. So 5, I now know that x plus y plus z is equal to x plus z. That was using the rule of identity, and we were substituting 4 into 3. So identity on 3 and 4, and now this is dependent upon 1 with x and y, axiom 3, and axiom 8. Okay,
So you're trying to get.
did I mess up?
I think you're trying to get x plus z, right? That's where you're going with it.
Yeah, because x plus z equals 0.
You don't want y plus z, you want x plus z.
Oh my goodness, why'd you guys let me do that?
I figured you could just add somewhere you were going with it.
Should have added z on the other side.
Yeah.
Can we do this?
Wait, you can still fix this.
It would have also worked if we did z plus x plus y is equal to z plus x, right? And then associativity down here, we would be saying, gotta change the order. We would be saying that z plus x plus y is equal to z plus x plus y.
Wait.
Using axiom 3.
And now, substituting up here,
Gotcha.
we have z plus x plus y is equal to z plus x.
Wait,
Oh, sugar.
I'm missing something.
We still have x plus z, not z plus x.
Isn't, you can switch.
Just
with
use
one of the
axiom
axioms.
1, yeah.
Yeah.
You could have done that instead of having to erase everything.
6. No, because we had the order wrong and the wrong things associated. Probably still a little bit faster, just made the proof longer. Okay. we know that x plus z is equal to z plus x. That's axiom 1. Axiom 1. Okay, so we can swap the order now. So 7, using identity, we can substitute x plus z in for z plus x in there. So then we get x plus z plus y is equal to x plus z. That was using identity on 5 and 6. And now we're using 1 with y variables, axiom 1, axiom 3, axiom 8. Okay, now what?
Now you use your associativity, right? Or do you use substitution first?
Now we get
You just
substitution.
substitute right in, right? Yep, 0 plus
Substituting
y
in
is
0. 8. We
Switch
definitely did this long way. Okay, so then 0 plus y
While he's using axiom 8.
is equal to 0 using identity on lines 2 and 7. And we have same axioms up there.
Yeah. Yeah.
Okay. Now I know y plus 0 is equal to
Why?
y. Not that 0 plus y is equal to y. So another annoying thing, I know that 0 plus y is equal to y plus 0. That is using
Axiom,
axiom 1.
right?
Axiom 1, yeah, addition is commutative. We're still, that's only dependent on axiom 1 for its validity. Okay. Now I can make that substitution there. So 10. So now I know y plus 0.
You didn't need to switch it from axiom 6.
This one says x plus 0 is equal to
Okay,
x.
sorry.
It doesn't say 0 plus x is equal to x.
Yeah.
It says x plus 0 is equal to x. That could matter.
I rather
It happens not to matter, but could have been the case. Okay, so now I know y plus 0 is equal to 0. Wait. Is equal to 0 plus y. Oh, no, I substituted. Yeah, so that, I did a substitution between these two. So I was using identity on 8 and 9. And now my axioms are 1 with xy, a1, a3, and a8. Okay. Now I can use the fact that y plus 0 is equal to y. That's by which axiom?
6.
Axiom 6. And this is only dependent upon axiom 6 for its validity. Okay, now substituting into here, I can replace y plus 0 with y. So then I get 12. Y is equal to 0. That is using identity on 10 and 11. And we have 1 with xy, axiom 1, axiom 3, and axiom 8.
And axiom 6, right?
And axiom 6. Okay. And there we did it. We showed that this implies this. So, 13, we showed that x plus y equals x implies y is equal to 0, conditional proof. And now we have as our axioms, we remove 1 as a premise. And so now we're just dependent upon a1, a3, a6, and a8. And then we can universally generalize. And now we can say for all x and y
In R.
in R, x plus y equal to x implies y is equal to 0. That was universal generalization on 13. And it's dependent upon the same things for its validity. And we're done. Since we were only dependent upon the axioms when it was all said and done, and we proved its consequence of the axioms. So it's a theorem. Okay, that was a nightmare. Now we go to informal proof. Come on. Something you got it right. grab some of my own markers and forgot. Alright, so let's reprove this more informally. Informally, how might we say this? We're proving if x plus y is equal to x, then y is equal to 0. That's where you might see it in math text, the exact same problem. Remember that it's understood, going back to, you might say, whoa, wait a second, we didn't add our universal quantifiers. It's an understanding we have in English that when we don't use the quantifiers, they're idiomatically there. It's just implied that you put them there. So it's just understood that this is the same. For all real numbers, x and y, this is the case. And we rarely bother specifying that. Make sense? All right, so we're trying to prove an implication. How do we prove an implication?
Assume the antecedent.
Assume the antecedent. So line 1, how do we assume an antecedent informally?
You say
1. You say let.
Assume it.
Let whatever's right here. Let x plus y be 0. If we're worried that maybe it wasn't specifically clear what the domain is, we'll often say, let x and y be real numbers. Let x and y in R such that x plus y is equal to x. Right? 2. Then
Axiom 8, right?
yeah, then by axiom 8, comma, there must exist z in R such that it was the additive inverse for x. X plus z equals 0. Then by axiom 8, there exists z in R such that, I'm going to do s dot t dot all the time for such that, x plus z equals 0. Good?
Yeah.
3. Then, from x plus y equals x, here's my own, by the way, should probably say a lot about this as we're going through this. This has a ton of my own flavor to it. So a lot of authors who do mathematical proofs, they just like write out a paragraph explaining everything. The fact that I'm putting numbers here, numbering each line, and on each line I only put a single sentence, that's my own flavor. That's not something that's universally the case for informal proofs. So some of these things are my own flavor, and you're about to get something else that's my own flavor. I use an arrow all the time for implies. So x plus y equals 0, that gives us that x plus y, let's do it smarter this time. Where did we want the z?
You wanted it.
X plus z equals 0. So maybe I'll swap the y first, and then we'll add the x. There we go. So then y plus x is equal to x. I just swapped the order there. A lot of the times, if it's obvious what I did, I won't bother specifying it. The justification for going from here to here is
Axiom 1.
axiom 1. Axiom 1 says we can change the order, which then gives me that y plus x plus z is equal to x plus z. That's just using logic. You can add the same thing to both sides. That's not an axiom. Right? Now I use associativity here to group my x and my z together. So that gives me that. Maybe I'll just write it down here. So that gives me that y plus x plus z is equal to x plus z, which gives me that y plus 0 is equal to 0, which gives me that y is equal to 0. And we're done. So I just really showed if this was the case, then this was the case. And it's all good. And we don't go through the steps again of, so notice that all we really did was did from this step to this step and called it good, because the steps after that are kind of trivial.
Yeah.
Right? So we don't bother writing out. Therefore, we showed if this is the case, then this is the case, and therefore it's always the case that if this is the case, then that's the case. You can write that out if you want. Or something else that I will often do as my own style, I'll put as a separate line for, therefore, on my last line, therefore, y is equal to 0, square box. Just as a reminder to the reader, hey, that's what we were after, remember? Okay, so there's our first informal proof. Oh goodness. Maybe you'll be my friend. We can start setting aside markers that were just worthless. Okay. Theorem 1, we did it. Theorem 2, what does theorem 2 say? Someone read it to me?
You want, for all x and y and r, if you're trying to get the exact thing, what would you the idea?
Just read it to me.
For all x, y, and r.
Okay? Oh, there it is. For all x, y, and r,
X is not equal to 0, and x
Is-
times y is equal
x
to
is not equal to 0, and what?
X times y is equal to x.
And x times y is equal to x,
Then y is equal to 1.
then y equals 1. Oh, so this is basically an identical proof.
Yeah.
Alright, so 1, assume the antecedent. Let x and y be real numbers such that x is not equal to 0 and x times y is equal to x. Okay, now what?
This time you're going to use axioms.
Axiom 9? No,
I'm guessing 9.
No.
Yeah.
9.
9.
9! What does axiom 9 say?
There exists a y such that x times y equals 1.
It says, for any number x, as long as x isn't 0,
Which it isn't.
then we're guaranteed that there is some other number out there that we can multiply x by, such that we get 1.
So we're going to say there exists a z.
Right, so 2. So since x is not equal to 0, maybe remind them that that was a condition. Since x is not equal to 0, then there must exist z in R such that x times z is equal to 1 by axiom 9?
Mm-hmm.
Right? Okay, now what?
Multiply z to each side.
Yeah, multiply z to each side. 3. Then x times y times z, time to start getting real lazy now, is equal to x times z. Notice, strictly speaking, that's nonsense. And when I talk about x times y, then times z, or y times z, then times x, because times is a binary operator. I gotta give it 2 terms. You can't just plug it in the middle of 2 things and have it make sense. But we're gonna write some nonsense. I mean, assume you can understand it. Okay. So then x times y is equal to x times z, which gives me that y times x times z is equal to x times z.
By identity, you know x times z is 1.
by assumption,
by
I know that x times z is 1.
axiom 9, so.
Or not by assumption. Yeah, basically by definition of z in here. What was z? It was the unique number I could multiply x by to get 1. I was guaranteed there was such a number by axiom 9. So whatever that number is, we're just calling it z. Okay, so I know x times z is equal to 1. So that gives me that y times 1 is equal to 1. Which gives me that y is equal to 1.
Oh, and that's using axiom 7, right?
Using the fact that 1 is a multiplicative identity,
Which is axiom 7.
which is axiom 7, yes. So that was using axiom 7. Therefore, y is equal to 1, and we're done. Good?
Yep.
All right, next one. What is the goal? Maybe let's say a little bit about that. What is the goal in an informal proof? What are you trying to communicate?
You're supposed to have a degree of rigor to show that your assumptions lead to your conclusions.
You want to have, so we call it the idea of the proof. The idea of the proof here was to multiply both sides by x's multiplicative inverse. Multiply both sides by the z thing that gave us the 1. That was the idea. Once you got the idea, you kind of figure out how to do the proof. So what we're after is you want to put enough on paper that you feel like someone could, if they had to, take it from this to an actual rigorous proof. And so you want to capture any of the steps that weren't obvious steps and try to make those explicit. A generally good rule of thumb in a class is you want to prove it well enough that the person to your left could do this with your proof.
Okay?
That's a general rule of thumb. So enough that you could prove it rigorously if you had to. That's what we're after. And so trying to make sure you get a big picture idea of what's going on in the proof. Okay. That's great. Next. See if this has anything in. What's our next one?
If x plus y is equal to x plus z,
If x plus y is equal to x plus z,
then
then
y is equal to z.
y is equal to z. Okay, so this is the converse of what we get from logic. I know if y equals z, then x plus y equals x plus z. I know that from logic. This implies this is true from logic, but this implies this is not true from logic. This may or may not be something that's true in our system. Make sense?
Yeah.
Okay, so proving the converse of something we have from logic. All right. How are we going to prove it?
Yeah.
What do we start with?
Antecedent.
Let the antecedent. Let x and y and z be real numbers such that x plus y is equal to x plus z. Okay, now what?
You might want to use the multiplicative identity. So you'd add another number, and then you could, oh no, that wouldn't work. Never mind.
I know you would have to use axiom 3.
We haven't talked about subtraction, so I'm trying to figure this out.
We haven't talked about subtraction. We did subtraction. Over here I had x plus y is equal to x. And what did I do? I showed y is equal to 0. Or in short, what did I do? I subtracted x from both sides. Big picture, that's what I
You
did.
did the exact same thing.
But I did it in a really roundabout way. How did I subtract x from both sides?
You used axiom 8.
I used axiom 8. I used the fact that for any number out there exists some other number such that their sum is 0.
So that's what I was thinking, not multiplicative, but yeah.
So I am guaranteed that there is some number out there, what should we call it?
A.
week is that? So then there must exist some number.
Sure.
We used x, y, and z. We'll call it u. There must exist some number u in the real numbers such that x plus u is equal to 0. X is a real number, so there must be some other real number out there, we'll call it u, such that x plus u is equal to 0.
Okay, I see.
Right? And we know that from which axiom was it?
8.
We get that from axiom 8. Okay, now what?
Now you
Add u to each side.
yeah.
Add u to both sides up here. Then x plus y plus u is equal to x plus z plus u, right? Reordering and grouping terms, I get y plus x plus u is equal to z plus x plus u. Now what's x plus u?
0.
X plus u is 0. So then we get y plus 0 is equal to z plus 0. Or in other words, y is equal to z. Therefore, y equals z, and we're done. And this marker is done. Maybe we'll move to the whiteboard, or chalkboard. Use chalk instead.
In our system of arithmetic, do we also get right-hand cancellation? We just proved left-hand cancellation. I know that in group theory we didn't get both of them.
We do get it in arithmetic, and you can prove it trivially as a corollary now, because of commutativity.
Right, so we can use that now, though.
Yeah. So
Okay.
if we want, we can throw that up as a corollary real quick. Which one did we just do? Did we do right-hand cancellation or left?
Left-hand.
We did left-hand, so let's do it as a corollary real quick. So quick corollary. I already forgot which one you said. We did right-hand or left-hand
We
cancellation?
did left-hand.
Left-hand cancellation. So now we want right-hand cancellation. If y plus x is equal to z plus x, then y is equal to z, right? Sorry. Mixing two notations. Then y is equal to z. Okay, that's what we want to prove. 1, let x, y, and z in R such that y plus x is equal to z plus x. 2, then x plus y is equal to x plus z, using axiom 1, the fact that addition is commutative, which gives me that y is equal to z by theorem. What was the last theorem we just did?
3.
By theorem 3. Theorem 3 said if x plus y equals x plus z, then y equals z. Okay, so now we have that. All right, so what's our next theorem? Guess it's theorem 4 now. What does theorem 4 say?
X times 0 is equal to 0 for any x.
We want to show that for all x, x times 0 is equal to 0. Right?
Yeah.
All right. So this one, where do we start? We don't have an implication.
You would let some number in R.
I need to show that this is true for every, sorry, let me rewrite it slightly different, for all x in R. I think it was understood. I don't really need that. I think you guys understood me. Okay, but that's what we're showing.
You-
So I need to show it for any real number R you choose. This is always the case. So I start by let x be any real number. Let x in R. Which number is it? I have no clue. And having no clue which number it is in R, I need to prove that when I multiply it by 0, I still get 0.
Okay.
All right. This one's kind of a weird one.
Would you use
I have an
axiom
idea on
9
how
at
to
all?
do it. Sorry, what?
Said, would you use axiom 9 at all?
Axiom 9? No, I don't think so. Not the way I see to do it. I'm going to use a cancellation law and distribution the way I'm thinking about doing it. I'll show you my way.
Okay.
I don't know how to give you good intuition for this one. This one, kind of curious if you guys come up with a different way. So then, let's start with x times 0 plus 0 and see what that equals. And I know it feels like an arbitrary starting point,
Okay.
but it's because I'm going to be using left-hand cancellation and ending up with 0 equals x times 0. That's big picture where I'm going. Okay, so x times 0 plus 0 is x times 0. Anything plus 0 is just that thing.
Yes.
So this is just
Okay.
x times 0.
You
Oh.
did the same thing that you did.
Before we do that, let me make an observation. So let me make an observation first. Observe that 0 plus 0 is equal to 2. Oh wait, no it's not. What's 0 plus 0?
0.
0, how do you know?
Because of axiom 6.
Axiom 6. Axiom 6 says anything plus 0 is just that thing. 0 is a thing, so 0 plus 0 is just 0. That's how we know. Okay, so now I'll continue with the idea I had. So then, x times 0 plus 0 is equal to, anything plus 0 is just that thing. So that's equal to just x times 0, which is equal to x times 0,
And then you distribute.
which is equal to x times 0 plus x times 0, using distribution. And now I got something plus 0 is equal to that same thing plus x times 0. So I can do my left-hand cancellation, and I get 0 equals x times 0.
Yep.
So for, as a general rule, you typically need to use a previous theorem to prove the next theorem. Usually they line them up that way. So then by theorem 3, x by theorem 3, 0 is equal to x times 0. We can do our left-hand cancellation, and we're left with that equals that. Which is what we were after. So I just barely showed x times 0 is always equal to 0. Good?
Yeah.
All right, what's our next one?
Just verify.
What does it say?
There exists a unique y in R such that x plus y equals 0.
Okay, so this one says for all x, there exists one and only one y. There exists a unique y such that x plus y is equal to 0. How's that different from axiom 6?
As it says, there's only one.
Yeah, axiom 6 says for any x there exists a y such that x plus y equals 0. Now we're going to prove, and there's only one y. There aren't secretly two numbers I could have added to x to get 0. There's only one other number in the whole set I could have added to x to get 0. For any number x. All right, so 1. Let x be any number okay, and how are we going to prove this? We're going to do by way of contradiction. I'm going to assume that there is more than one thing I can add to x to get 0, and show that leads to contradiction.
Is that the typical way to do unique proofs?
That's one way you can do it. Or you can show that I know that something satisfies this, and then I can show that anything else that satisfies this is really just that same thing.
Okay.
So, two ways we can do it. We're going to do it the proof by contradiction way. I'm going to assume that it's not the case that there's only one y. What's the opposite of there being only one thing?
There's at least 2.
There's at least two things.
Okay.
Right?
Yeah.
So let x in R, comma, and assume by way of contradiction, maybe we'll put a line in here really quick, that there exists both y and z in R such that x plus y equals 0, x plus z equals 0, and y and z are two different numbers. So assume by way of contradiction that there are two numbers out there called y and z, such that when I add them to x I get 0, but that they're two different numbers.
Okay.
And we're going to prove that therefore y is equal to z, and so they're the same number. That's our contradiction. And therefore there's only one number that satisfies it. Because there being two numbers that satisfy it leads to contradiction.
Gotcha.
Okay. So assume by way of contradiction that there are two numbers, y and z in R, such that x plus y gives you 0, and x plus z gives you 0, and y and z are actually different numbers. They're not secretly the same number. Okay, 2. Then, I know x plus z is equal to 0, and I know x plus y is equal to 0.
So you know they're equal to each other.
So I know that this is equal to this. Because equality is transitive. I know that if A equals B and B equals C, then A equals C. We proved that as a theorem of logic. I know if this equals this, and this equals this, then this equals this.
Is that not just the substitution rule?
We use substitution to prove it. It was next to trivial.
They're two separate things. Okay.
Use the rule directly or use the two-line proof. All right. So then, x plus y is equal to x plus z. Right? Then what?
Left-hand cancellation?
Then using our left-hand cancellation, we get then y is equal to z. Contradiction.
So nice to know how
Because
use
y is
that.
not equal to z, y is equal to z. 3. Therefore, there must only exist one thing y in R such that x plus y equals 0. There couldn't have been two or more things. Because there just being two gives us a contradiction. Good there?
I'm not understanding the difference between left-hand and right-hand cancellation. What do you mean by that?
We had the same thing plus different things are equal.
I have to
So
have
we
one.
can,
Thank
okay,
you.
yep. So we can cancel out the left-hand thing.
Yeah.
That was theorem 3. Theorem 3 said if x plus y is equal to x plus z, then y is equal to z.
Oh, you mean between those two terms?
So that was using theorem 3. Theorem 3, sorry, she's used this terminology. The high-level terminology for that is, that's our left-hand cancellation law, or our left-hand cancellation theorem. And we did as a corollary, a right-hand cancellation theorem, in case we ever want to do that. So those are two things we now know we can do. Anything else that was weird? Cool. That was theorem 5. What's theorem 6?
There's a definition of note before you get to theorem 6.
Oh. Definition. It's off the camera, so I should probably rewrite it. Okay, so our definition is that for all x and y, we say, did I define negative x or negative y?
Negative x to y.
Negative x equals y if and only if x plus y equals 0. All right, let's explain this. I just barely proved, up here on the previous line, I just barely proved that for any number x, there exists one and only one y, such that their sum is 0. So since we're naming one and only one thing satisfies this, we can name it. We can give it a name. We can give it a definition. And that's what we mean by negative x. So negative x equals y. Here's what we're defining. Colon on the side of the definiendum, right? The new symbol. So we're defining this in terms of this. What do I mean by negative x? I mean the one and only one number I can plug in here to make this equation true. So what is negative 3? It is the one and only number you can add to 3 such that their sum is 0. That's the definition of negative 3. It's the additive inverse. We call this the additive inverse. Negative, sometimes we say the additive inverse. So negative 3 is the additive inverse of 3. It is the one and only number that you can add to 3 to get 0. There is no other one. So up here we proved for any x, there exists one and only one y that we can add to it to get 0. And since it's one and only one thing, we can name it. We can define it. If it was multiple things, we couldn't. If you said, who's James? And I said he's the person in the classroom. That doesn't tell me who James is. Unless there was one and only one person in the classroom. Then you now know who James is. So what is negative x? It only makes sense as the additive inverse of x if there's only one thing that satisfies that, which is what we proved up here. So oftentimes before these types of definitions, you'll get a uniqueness theorem. We proved that there's one and only one thing that satisfies this, and then we can define that thing.
So there really isn't subtraction in...
We'll define subtraction,
Oh, okay.
but we define it in terms of these primitives. I don't know what you mean by really is. Subtraction is defined in terms of addition. Division is defined in terms of multiplication.
So this isn't defining subtraction, it's just defining...
This isn't defining subtraction, this is defining the additive inverse. This is defining the negative symbol that we use.
Right.
Now, negative and subtraction are very closely related, and we'll see what that relationship is, but they're two different things.
Oh, okay.
Negative is a unary operator. It's something that you apply to one number. I take 3, I make it negative. That's negative 3. So it's an operator. You spit in 3, it spits out negative 3.
Oh,
Subtraction is a binary operator. It takes two numbers and calculates their difference.
okay.
One way that you can define subtraction is you can say x minus y. We define that to mean x plus negative y. And that's one way to define it.
Right, that's why I thought that all of them were...
Yep. So that's all very natural. Okay. So that was our definition. And so I made a note over there. We'll note it again. Note now we have a definition for some new numbers. I now have a definition for negative 0, and negative 1, and negative 2. and negative 3, etc. And those are numbers that we now know are real numbers. Since 3 is a real number, negative 3 has to be a real number. Because every real number has a unique additive inverse. Wait, I said 0 and I also said negative 0. Are those different numbers?
Not necessarily.
No, they're not, and we'll prove that they're the same number. So 0 is its own additive inverse. Nothing wrong with that.
But it still belongs to that side.
It's in the real numbers. Negative 0 is in the real numbers. Because 0 is in the real numbers.
Yeah.
Just so happens we have two different names for the same thing. The same way that this is another name for 4.
Which is why it's important to say 0 is not equal to 1.
It was important to say that, yeah.
It seems like they figured all this out, and then like way later they discovered that there was a good axiom, and they put it way down the bottom. Just
The order that those are put in is in no way tied to historical events.
dang it.
Somewhat arbitrary.
So you
Because we can split those up, and removing all the ones that have the less than operator, we call those the field axioms. And those, it turns out, are an interpretation for a particular set of axioms that prove everything with fields. The same way we have groups, we have the concept of a field. So, yeah, the order there is somewhat arbitrary. Theorem 6, right? I don't know if we can squeeze it in here. What is theorem 6?
For all x, negative x equals x.
For all x, okay. Then the additive inverse of the additive inverse of x is just x. What are we saying there? I know that for any real number, there's a unique number you can add to it to get 0. So if I start with 3, 3 plus what gives me 0? Well, by definition, it's negative 3. Right? Similarly, I know that negative 3 plus something has to give me 0. What's the number I put here? It's negative 3. And now what we're going to prove is, it turns out that negative 3 isn't a new number. It's just 3. That's what we're proving. So this isn't actually a different number that we're adding to our system. We already had this number. This is just a different name for the same number. The same way that 2 plus 2 was just a different name for 4. Different way of writing 4, that's a different way of writing 3. Or negative x, just a different way of writing x. That's what we're proving.
So you're saying negative 3 is like its own symbol, basically.
Well, if negative 3, look, going back, we showed that 1 plus 1 was not equal to 1. It was something different.
Yes.
And so we need to come up with a symbol for it. If negative 3 turned out to be something that we didn't already have a symbol for, we might want to come up with a symbol for it. But it turns out it is the same number as 3. In this case, they were the same. That's what we're showing. If it turned out to be different, then we need more symbols for it somehow to represent that number.
I get what you're saying.
Yeah. So we don't need to waste time coming up with new symbols for the additive inverse of the additive inverse, because we already have that symbol, turns out. It's just without any of the negatives. All right, so let's prove that.
But if that's the case, why did we do? Why do we allow negative 0 and 0 to exist in the same domain? Essentially.
We're going to show that having negative 0 as a separate symbol is completely useless. And no one ever actually writes negative 0, because it's just 0. But we haven't proven that yet. So thus far, is negative 0 equal to 0? We don't know yet. Maybe that is something different. Maybe it's not.
Okay.
We're going to prove it. I think it's one of our theorems.
It's right after this.
It's right after this. So we're going to prove that those are actually equal to each other, and we don't need a special symbol negative 0. And we can just use 0.
Okay.
All right. So sticking with this one. 1. Let x be any real number. And observe that. Let's see. Negative x. I'm trying to show that this is ultimately equal to x. You with me? So what I'm going to do is I'm going to add 0 to it first. So that's the same thing as negative x plus 0, which is the same thing as negative x plus, here's a fun way we can write 0, negative x plus x, right? And now what can we do?
Negative x plus negative x.
Yeah, group
Is-
these two together.
Yeah.
This is going to be negative x plus its additive inverse. The negative of negative x. And what's any number plus its additive inverse? 0. So, that's equal to that is equal to, I guess a bracket here, negative x plus negative x plus x. So we have a number plus its additive inverse. We have a number plus the negative of that number. A number plus the negative of that number is always 0. So this is just equal to 0 plus x, which is equal to x. And we're done. We've already showed that negative x is equal to x. Make sense there? Cool.
Then you can just substitute 0 in for x and get your other group.
So, theorem, is it a theorem or a corollary?
It's corollary.
So, corollary.
Isn't there a theorem 7?
Yeah, theorem 7's next.
Oh.
Oh, theorem 7.
Sorry, I missed that. Yeah, you need them both.
What does theorem 7 want me to do?
Negative 1 times x equals negative x.
Negative 1 times x equals negative x. So I want to show that for all x. I want to show that for all x. There's a bracket. That's an x. For all x, negative 1 times x is equal to negative x. Okay. 1. Let x be a real number. Sorry, let me draw the in symbol nice one so you guys know what I keep writing. I'm trying to write that. It's like a C with a line straight through the middle. It's an epsilon symbol from the Greek alphabet. Blanked. Okay, so let x be any real number. Let x in the real numbers. 2. Then let's see. We're looking at negative 1 times x. And ultimately, I want to get that's equal to negative x. Okay. Well, I got somehow getting negative x to show up there. The only way I know to do that is to add a 0 and then make that 0 an x plus negative x. So this is equal to negative 1 times x plus 0, which is equal to negative 1 times x plus our fancy 0, which is x plus negative x. Right? So I got a negative x to show up. Now I need these two things to somehow cancel each other out, and I'll be left with the negative x and we're good. So that's equal to, let's group these two terms together, just so you see what I'm going to make cancel out. I need to make negative 1 times x plus x plus negative x. I need to somehow make this 0. Once this is 0, then I'll have negative 1 times x is equal to negative x, and I'll be done. So the goal now is to make that 0.
You can pull out the x.
Yeah. Now don't repeat that and see if anyone else can come up with what we should do.
Use the distributor property.
Use the distributive property. He understood you. Okay. So x is the same thing as
X times
1 times x. So this is equal to, we have negative 1 times x plus 1 times x plus negative x. So now I have something times x plus something times x. I can factor the x out using the distributive property. The distributive property says, oh, it's on the left-hand side here.
Does that matter?
No. Hopefully you see how it doesn't matter. Hopefully you can follow what I'm doing now. What line was it?
Do we ever do a proof where we show that you can flip the side that you're on?
It would be trivial. It would be start with unflipped, use commutativity to flip it, then distribute.
What I'm wondering is if there's a proof for that, you can do it in no matter what's on the left or right hand side.
You can prove it. You'd just be using commutativity.
Okay.
Okay. So, what does the distributive law says? It says x times y plus z is the same thing as x times y plus x times z. When we go this way, we call it factoring out the x. When we go this way, we call it distribute the x in. I have two terms like this with an x. I'm going to factor the x out and rewrite it this way. Sorry, that was off camera. Probably should have explained over here. So I'm going to factor the x out of these two terms. And so this is going to be equal to, using that property, is going to be x times the sum of these two things, negative 1 plus 1. So I factored the x out of these two terms, and then we still have plus that. Plus negative x. Everyone follow what I did from here to here? Just using distributive property. Commutative property first. First I need to flip the order so that the x's were over here, then factor them out to use the property correctly. Okay, now negative 1 plus 1 is?
0.
0. Anything plus its additive inverse is always 0. It's additive identity. And so this is equal to x times 0 plus negative x. Okay, what is x times 0?
0.
How do you know?
This is what we just proved.
Theorem
6. Or
something.
before that. Theorem 4.
Theorem 4, right here. So, x times 0 is 0, so we get 0 plus negative x. What is 0 plus negative x?
Negative x.
Just negative x. 0 is the additive identity. That just gives me negative x. And in case you lost track of what we were saying, therefore, negative 1 times x is equal to negative x. That's what we were after. Any questions on that one? Cool. Now was the corollary, right?
Yes.
Corollary. 0 is equal to negative 0. Let's prove it. I know that negative 0 is equal to what? What is negative 0 equal to?
Negative 1 times 0.
Negative 1 times 0. It's equal to negative 1 times 0. What is anything times 0? 0. That's what we mean by corollary. You practically get it for free. So negative 0 equals 0. Wonderful. Okay, what's next? We're on theorem 8. Someone want to read it to me?
For all x, y, negative x times negative y equals x times y.
For all x, y, any brackets then, negative x times negative y is equal to x times y.
You can pull the two negative ones out.
But I can't combine them into one. I don't know that negative 1 times negative 1 is 1.
Yeah.
I may use this to prove that. That's going to be a corollary to this.
I feel like we're doing in a roundabout way. With theorem 7, we know negative 1 times anything is just negative of that thing, so negative negative 1 is 1.
Oh, I see what you're saying.
Yeah.
I think that works. So let's do -1 times -1 equals 1 as a lemma first. Good chance for a lemma here. Rather than as a corollary of the theorem, we were going to make it an obvious consequence of the theorem. Now instead we decided it's going to be some small proof that we use to help us prove our theorem. So I'm going to prove that -1 times -1 is equal to 1. Okay. So -1 times -1 is equal to, using our previous theorem, -1 times something is equal to the negative of that thing. So -1 times something is equal to the negative of that thing. Hopefully you can see both those minus signs, the negative of that thing. But then, using our theorem down here, negative x is just x. So that's just equal to 1. Cool. That was much easier than the way I was thinking. So then we get as theorem 8, theorem 8, we're trying to show that -x times -y is equal to x times y. 1. Let x and y be any two real numbers. 2. Then -x times -y. We can -x, we can rewrite that as -1 times x, and -y, we can rewrite that as -1 times y. So this is equal to, I'll use brackets to try and keep all the thinking clear here. That's equal to -1 times x times -1 times y. Right? And now I know that multiplication is both associative and commutative. So I'm going to be able to move the 1 over here with the x, or basically I'm going to be able to swap the x and the 1, -1 there. So that is equal to -1 times -1 times x times y. Right? And now we use our lemma up here, -1 times -1 is equal to 1. So using our lemma, we get that's equal to 1 times x times y, which is just equal to x times y. Cool. I have to update my notes. It's backwards from the order I usually do it, which means I have a terrible way of doing it, whatever it was. It's one of the good things about proving this in class. It's one of the bad things about never doing this in college. I just have my own proofs. Okay, next.
Is there even classes in college where you do this? Without going, not in your master's program or something?
It can kind of be dumped on you at the beginning of a real analysis course, but then it's just dumped as a bunch of homework problems.
Yeah.
And so you never see anyone do it.
Yeah.
And the teacher just says if you did it right or not.
I guess it's a good thing we're in your class right now. If we ever want to take those kind of classes.
Yeah,
Whatever
since
that's
all of
called.
you plan on going and getting advanced math degrees. Yeah, I know you must be tired of nursing by now.
I'm getting there.
Teach math at university, cush job.
Is that where you were headed?
No. No, being a teacher does not pay near as well as programming. Like, I can't remember what my professors told me at Dixie, but they told me that they cap out at like 76,000 a year, something like that.
Really? That kind of surprises me.
Lower or higher?
Higher. I thought it'd be higher.
You thought it'd be higher. Yeah, I thought it'd be higher too.
I
Now,
guess it depends on the university.
I was talking to them quarterback when I was in college. I don't know how it's changed.
I bet at a different university it's more.
Oh yeah, I'm sure it changed from university to university. But one of my professors was telling me that when he heard how much he was gonna make, he thought it sounded like a lot until he started making that much. He was like, I made a wrong choice.
Well, you gotta do it for the money, I guess.
Well, he didn't do it for the money, but he thought money would be something that he wouldn't have to worry about. And so, sole income earner for a family of, I think he has 4, he thought, that should be plenty of money. Turned out to be more of a pinch than he realized.
Yeah.
Anyways,
I have a question.
Go ahead.
I lost it. Oh, I have a hard, like, when it comes to, if these were homework problems, for instance, I would have an incredibly hard time coming up with ways to prove these theorems. And what is it like? What is a mental procedure that you would go through to try to, like the pattern to solve these?
so the pattern to prove something is that there is no pattern. Provably, there can't be any pattern.
Well,
and so there are some general techniques that you apply, but when you get to further on in proofs, it's just, you just gotta have the epiphany. So
Yeah.
with all the problems you solve, you just have to have that breakthrough moment. Like for the harder problems I had to solve when I was going to college, I had a whiteboard in my room. I'd write on my whiteboard and it'd be the first thing I looked at every morning, and I just waiting for that new idea, that connection, that maybe this will work type thing.
Yeah, those sound like you just have to try out every single scenario until it makes sense.
But, well, there is no such thing as trying every scenario, provably, which is the danger.
That's not what I mean necessarily.
I know.
Like, what axiom do we plug in? Who knows? Which one do you apply to then try it out? It's
Right.
your guess is. I mean, my guess is any
So,
one of them.
So there isn't an answer to that. There are some general techniques. So one is, if you're proving an implication, start by assuming the antecedent.
Yeah, that'll always be the fun part of homework. I gotta write down the first step and then stay
Yeah.
for an hour.
Sometimes when you're doing a proof, it helps to write what it is you're trying to prove and then kind of reverse engineer it a little bit. Like, what would I need if I were to prove this? For some of these, I'm just trying to get the thing that I want to show up, pop up in there. So I know I'm trying to get this equal to this. So I'm going to start with this. And I need to force that to show up somehow. And so my thought process there is, I'm just going to start with this. I need that to show up. Well, the only thing I can do to this without changing it is multiply it by 1 or add 0. That's all I can do. So I added 0, and I added 0 in such a way that that term would show up. Then once I got that term to show up, I know that these other terms must cancel out somehow. Because I know I'm banking on the fact that I'm not proving something impossible. And so I'm banking on the fact that since it showed up over here, since I got this is equal to a bunch of terms and that, those other bunch of terms must cancel out somehow. So now I'm just looking for how they could cancel out.
Just sounds like just takes a lot of practice and.
It's at the end of the day, it's just seeing the connection. It's like you get good at programming abstractions, and someone says, "So, what's the thought process for how you're supposed to program an abstraction?" You think about what you want to do and the smart way to do it.
Yeah, I honestly, yeah, I couldn't tell you. Then it just
Right.
hours and hours and hours
You just gotta
Thinking about it.
think about it. Keep thinking.
for like way more time than I have.
So, oftentimes, unfortunately, that's the best answer. How do you solve it? You just keep thinking about it. And you wait for that epiphany, that connection, that idea, and you'll have like 5 of those, and it turns out they won't work out. But the 6th one, you can bank on that.
6 times sure.
No, it's somewhat arbitrary. Sometimes you think you have an idea, turns out it doesn't work. So, yeah, that's the beauty of proofs. I don't need that vertical line. It's the thing that provably computers can't do. So humans have to do it. Computers can determine logical implications, but There is no procedure for proving things.
I don't know if it would be a great time to bring it up, but the last class I was in 3 classes ago, we talked about something that our human brain could solve logically, but the computers couldn't.
Oh, we touched on the incompleteness theorem.
Yes, and I watched the video,
Okay.
and it's funny because I've actually watched it before, a long time ago.
It's an amazing video. It
It
did a
is.
great job explaining it.
He did. Very talented. He's a great guy. I watched a lot of stuff. But what was kind of interesting is I didn't necessarily see anywhere that the brain was able to prove any of those incompleteness theorems, because it was like we could just say, oh, we tried out a whole bunch of scenarios and it worked out, but that didn't prove it. Like our brain says that's fine.
So he walked you through the process of coming up with a big Gödel number.
Yeah, I remember
And
that one.
that big Gödel number, when you look at its prime factorization, it doesn't come from any of the existing axioms. So it's not a logical implication of them. And here's the intuition for what that Gödel number says. This statement has no proof that it's true. Let's assume that this is false. If this is false, then it has a proof that it's true. So if it's false, then it's true. So it can't be false. So this statement is true. But what is this statement saying? It's saying that it's a statement that has no proof that it's true. You cannot deduce that this is true starting with the axioms. There's no procedure. If you were trying to prove this, and you tried all those axioms in every possible combination over and over and over again, every possible way that you could possibly do it, you would have never ultimately came to the implication that this is true.
Okay, are you implying that we can prove this is true with our mind?
We can understand that this is true.
We can understand that it's true, but a computer cannot prove it.
But there is no proof that this is true.
So there is no algorithm, essentially, or
There is no combination of axioms that you could take. Trying all the combinations. Trying this one, then that one, then that one, then that one, then this one, then that one, and all the possible different combinations, putting them together in every possible way that you could think of. Trying it on forever and ever to infinity. Computer churning away forever. It would never come to this conclusion that this is true. Because it's not a logical implication of the axioms. So there's no way to prove that's true. And yet we can understand, humans can understand that it's true.
I don't know. I think we're just gonna put that on the shelf for now.
It's a big pill to swallow the first time you come across it.
Yeah, well, he brought up a ton of different ones, and it was just in thought to me was that we might think it is, or our brain says, oh, that makes intuitive sense, and at the end of the day, it wasn't provable. It was not provable. But and your implication was that there's some mechanism in my brain that is able to essentially understand that something is proven true without being able to prove it with an algorithm.
Here's human understanding. Here's proofs. Proofs are some of the things that we can understand. Turns out we can understand things that don't have proofs.
That's where I'm having a hard time.
The Gödel statement that he came up with is an example.
I get this example. I get what you explained. I don't. It hasn't clicked something. But I don't. Like I said, maybe I'll bring it up when it's more appropriate.
I mean, it is unintuitive. It was a very surprising result. No one really expected that to be the result. Because one of the things he also talked about is he talks about David Hilbert. David Hilbert, arguably the greatest mathematician alive in the year 1900. And he gives his conference of all the problems that mathematicians are going to try and solve. And a bunch of the problems, it turns out, what's the answer to this? Yes or no? The answer is, it doesn't have an answer. And that kept being the answer to a bunch of the questions that he asked. Bad question, bad question, bad question. So very unintuitive. You're talking about an absolute genius thinking that these questions must have answers, and it turns out, no, they don't have answers. And provably they don't have answers. So, yeah, it's definitely not just going to appeal to your intuition. If it doesn't appeal to Hilbert, I don't expect it to just appeal to mine. But you can wrap your head around exactly what it is Gödel did. And what Gödel did, it's not all that complicated. The real thing that like the most advanced mathematics that you need, it's called the fundamental theorem of arithmetic. And it's just the idea that every positive whole number has a unique prime factorization. So looking at 28. 28 has a unique prime factorization. That is 2 times 2 times 7. Those are the unique primes such that when you multiply them together you get 28. And the way Gödel is setting up these statements, just intuition for it, is he's making so that he's using numbers to represent statements. And if you look at statement 28, then this is a consequence of using axiom 2 twice and axiom 7 once. Kind of.
Okay.
Really, he's encoding each individual term, but this is one way you could think about it to get intuition for it.
You're saying 2 and 7 are the axioms.
He used 2, he used axiom 2, axiom 2, axiom 7 to prove it.
Okay. To prove it. Okay.
To prove 28, statement 28.
Okay.
And so similarly, for any massive number, where does it come from? You look at its prime factorization. And that's ultimately breaking down where a statement comes from.
Yeah, I got.
And so you have some encoding of every possible mathematical statement into some big number. And then using its prime factorization, it's set up so that its prime factorization tells you where it came from.
Okay.
And then ultimately you get some big number representing some statement that's true that isn't a prime factorization of any of the axioms. And so you'd have to introduce it as an axiom if you want to extend your system. But then his procedure generalizes. And so even if you introduce a new statement that you came up with as an axiom, following his procedure, you can now come up with a new statement that can't be proven from those axioms. And you can extend the axioms again. And you can find a new statement and extend the axioms again and find a new statement.
Out of axioms, essentially.
I never want to say what happens to infinite, but for any big number of axioms you choose, we can always find some theorem, some conclusion that you could not have come to as a consequence of those axioms. As long as the axioms are complicated enough, which means that they're able to do arithmetic. Because it's using prime number factorization, the fundamental theorem of arithmetic,
Right.
to reason about. I don't know. Maybe watch it again.
Yeah, sounds like I need to get a little.
And get comfortable with prime number factorization, because that's the most actual advanced math used.
The video made way more sense since the last time I watched it.
And you did computation theory, right? Okay, so you should have some good intuition for what undecidable means as well.
I do, and I understand those ones.
Okay. Next, we were on theorem 9. What's theorem 9?
X minus y equals x plus negative y.
X minus y equals x plus negative y.
But there's a definition right for it that we
Yeah,
pulled up.
we have the subtraction.
Oh, because we got to define subtraction before we use it.
Yeah.
Okay, so definition. So now we define our subtraction symbol. Definition for all x and y and z, since we're doing it his way. Then x minus y equals z if and only if, colon on the side of the definiendum, x is equal to, did I say y plus z or z plus y?
Y plus Z.
Y plus z. All right, let's get intuition for what this means from our, just basically using it the way we know, subtraction. What is 8 minus 3 equal to? 5. And how would we prove that? Using this definition, we would show that 8 is equal to 3 plus 5.
Oh, okay.
That's what we're saying. These two things are logically equivalent. What do we mean by this? We mean this. Now, I hate that definition for subtraction.
Because it doesn't use the negative sign?
I think a billion times better definition for subtraction is that x minus y, we just define that to be x plus negative y.
Yeah.
And since I want to use it that way, I said, I'll give the definition the author gives, since I know you're all following along in the book, and I didn't want to confuse you. But then I'll put my definition in there as a theorem, so that I can use mine. So theorem 9, because it's logically equivalent. So I want to prove that for all x and y, x minus y is the same thing as x plus negative y. With me? So let x and y in z, not in z, in the real numbers, let x and y be real numbers, and let z be whatever their difference is. So let x minus y be z. With me so far? X and y are two random numbers, and we're letting z be their difference, because their difference has to be a number. By definition, what does that mean? X minus y equals z, by definition, means x is equal to y plus z. Then, x is equal to y plus z. I want to solve for z now. I know z is equal to x minus y. I'm trying to show that z is also equal to x plus negative y. So I want to get z by itself. How am I going to get z by itself?
Minus 2y from both sides.
Add negative y to both sides. Not minus y. Don't throw back in what we just replaced with our definition. Add negative y, you crazy kid. Okay, so add negative y to both sides, and that gives me that x plus negative y is equal to, I'll just say z, because y plus negative y is going to be 0, and we get z. So z is equal to x plus negative y, and z is equal to x minus y, therefore x minus y is equal to x plus negative y. And since we saw those words, we'll call it good enough. And so now I will use this as my definition for subtraction rather than his. Logically equivalent, I just think that this is prettier. 907. I don't know, should we keep going? It's a lot of proofs to do all in one go. I don't know if you guys are feeling burned out, you're not really following anymore, or you're just nodding along, nodding to keep yourself from falling asleep. And I think you're agreeing.
I'd be more engaged as far as doing these myself.
You want to do one?
I think it'd be cool to go around and try them.
All right,
that
feel
might
free.
be the slower process because it'll certainly take me some missed steps. But
Have at it, let's see what happens.
why is theorem 10 missing?
It's at the bottom.
Oh,
Because I accidentally wrote 11 before 10.
so do I do 11 first or 10?
Do 10 first.
Okay.
If the order matters, 10 will be better first.
Really quick, what is the difference between colon logically equivalent and colon equal?
Okay. So, this was a definition I should have put colon equal there.
Oh.
I would put colon equal there if that was my definition. So when you create a definition, you do a colon on the side that has the new symbol you're defining. So I was defining what this minus here means, so I put the colon on this side. And I'm defining it in terms of symbols that we already have defined. So what's on the right-hand side, you better already know what all those symbols are. What's on the left-hand side can have one new symbol.
Something new. Cool. So colon equals isn't a thing.
Colon equals is a thing. It's another way that I could define it if I would have done it as a definition. I shouldn't have had it as a theorem. I could have said definition x minus y colon equals x plus negative y. And as a definition, that makes sense. Here's the new symbol. Over here's just symbols you know. And when you create a definition, you will either always use a logically equivalent or an identity, an equals. And all definitions will use one of those two things, but we'll have a lot more to say about definitions when we get to chapter 8.
I see.
All right, so we are proving for all x, y, and z that x times y minus z is equal to x times y minus x times z. Let x and y and z be real numbers such that,
No, that's, yeah, it's like,
let x, y, and z be real numbers. Okay. You gotta talk to your students. Good practice for being a teacher.
I gotta learn how to write on a blackboard first. Well, I'm thinking that I'm gonna replace my minus sign with a negative, and then I'll have this be y minus plus negative z, and then I can use the distributive property.
Yeah. So he's gonna use the theorem I just proved to rewrite subtraction in terms of addition. And then we already know how to distribute with addition. Let me move our camera. Make sure that we don't lose him.
Is my handwriting too small, or is this legible? Whoops, yeah. Negative z.
So x times y minus z is the same thing as x times y plus negative z. Which then we can distribute. So that's x times y plus x times negative z. Now what are we going to do?
You could. I don't know if it's. I wonder if I'm thinking about it or not.
I think you're off to a good start.
Yeah, I'm off to a good start, but.
Sometimes we want to move around our negative signs.
Yeah, I want to.
And we know how to move around
I
products.
wanted to move this to here, but I'm thinking about what to do after that, and if it's just a dead end. But okay.
It's not a dead end.
Think about what step I would take after that, because I'm not sure which theorem I would use. I could do this, right?
So an x times y is equal to
That's
negative xz.
That's a
How did you
couple
get that?
It's a couple steps, I guess. Well, if you
Walk us through the couple steps.
well, okay. Is it useful for me to separate the 1 from there and say negative 1 times?
That's what I would do.
Okay, that's what I would do too. So I would do this.
Yes, I'll believe you.
Dots.
So he's rewriting negative z as negative 1 times z, and then I think he moved the negative 1 out front. So we know negative z is the same thing as negative 1 times z, we proved that. And then we know multiplication is commutative, so we can change the order. Okay.
Yeah. Now I'm trying to make the leap from here to here, and I don't know if that works.
Yeah.
So there's something I need to do.
There is something you could do.
Let me think
Just
about
adding
it.
a couple of parentheses could really help.
Okay. Not sure where they go. This-
Well, there's like only one term we want to mess with.
wait a minute.
Take your time.
What theorem am I supposed to use?
What theorem? We already used it once.
Is it theorem
You're going to
7?
use it in this theorem. Theorem 7.
Yeah, so that's what I was thinking, but I didn't know if that was okay. What I would do then would be like this, right? Is that right?
Negative. Okay, so then you got negative
Of
x
course, I
times
don't
z.
know if that's really useful.
I don't know if that's useful either.
Okay.
I know I sometimes prove something along those lines. I don't think we did today. That negative x times y is the same thing as negative xy. I don't think we did that. Yeah, I don't see that. So we didn't prove that, so I don't think that's helping.
Y is the same thing as x is y plus c. So in this case, I'm just gonna do a little scratch work.
All right.
If my definition is this, this would be an implied x minus y equals z would give us wait a minute, what was the one that you used?
I used the theorem right underneath it.
Oh,
You're saying that?
yeah, that's gonna be the easier way to do it.
Yeah. You already used that, didn't you?
How do I just do this though?
You don't want that.
There's- What's the one step? What's the step I'm missing?
You have -1
Oh.
times a number
There it is.
is
That's
equal
the-
to negative that number.
Okay. See that? That's the epiphany. Look at that.
That's the epiphany. X times z is just a term.
Ta-da. This spot on the blackboard's pretty, like, that's not gonna draw, so
Yeah.
you're just gonna have
There's
to
a bunch of those.
live with that. Right?
I think maybe people have better eyes than me.
X, Y,
X
minus
times
XZ.
y.
Yeah?
Yeah.
Did you skip?
No, I didn't skip anything, did I?
That's right.
Yeah, you skipped.
What did I skip?
You skipped that this is equal to x times y plus negative x times z. And if the negative there's throwing you off, you can put inner parentheses like that again, if that helps you. And then you can use that to there.
I forgot that I have to times by 1, basically. Or distribute into the negative.
So, yeah.
Because essentially.
-1 times x times z is the same thing as -1 times something. In your case, it's x times z is negative x times z. Okay, so then we got that. So then using this, x plus x, whatever you had, plus negative x plus z is the same thing as whatever minus x plus z. Or x times z.
Okay.
So, yeah, just that step missing.
These should be so simple.
There is a weird fact to math in difficulty of proofs. And proof difficulty goes like this. With how complex the material is. So your simplest proofs are just a pain for us to do. But then you get further on, so your foundations of algebra, it's kind of hard, getting into algebra, okay, everything becomes really, really easy, then more and more advanced stuff, and then suddenly it shoots off harder and harder again.
It's weird.
But so yeah, this early stuff, the stuff over here that we're doing, it's tough to prove.
But it's easy to understand once it's proved.
It's easy to understand. That's one of the things that kills us, is it is so intuitive, it's hard for us to think what to do next.
Yeah.
And it's not clear what to do next. Where when we get over to these ones, it's complex enough that there's kind of only one way to go.
So it's almost like our brains are designed for the middle ones.
Those are the ones we do really good with.
Yeah, that's interesting.
So like, foundations of algebra are kind of hard. By the time you're doing college algebra, intermediate algebra, college algebra, typical problems, yeah, not so bad. Then you go off and it gets harder and harder again.
Seems like if you could master proving these axioms and theorems, it's like you could be a master at algebra, basically, because it's the same concepts.
Algebra is in like college algebra. Yeah, this is about the hard stuff you do in college algebra.
So, great.
Working with matrices Q center. Okay. You guys want to call it there? More people want to do more problems. I just don't want to kill you guys.
Are we
So.
doing the rest of the part?
It's definitely
Yeah.
more engaging when you're the one doing it. At least, I mean, it's probably pretty boring to watch though.
I'm happy for you guys to be as engaged as you want to be.
I'm happy to continue.
Oh, my brain's shutting down, so.